My name is Katia and I'm a Year 11 student at Canberra Girls Grammar School. I will be exploring the first problem of the International Youth Physicists Tournament, Invent Yourself, which asks to create a non-invasive device that determines the direction of fluid flow inside an opaque pipe, and to optimize my device so that I can measure the smallest flow possible. When we first read this problem, we had no idea how to approach it. First, we explored the idea of using the phenomenon of the Doppler effect, but we decided against this, as using this phenomenon to measure direction of flow would be quite difficult. For example, it would only be effective with large amounts of flow, and could only be measured if the flow started after the device had started measuring. Anyway, we thought about using ultrasonic sensors instead, but again we found this approach not as effective for smaller flow rates, and came up against other limitations. We also explored the idea of using magnets, but then we came up with an even better idea. We thought of applying a heat source to the pipe and measuring temperature on either side, which ended up being our chosen approach. I'd just like to note that when we tested this, it is assumed that the liquid used is water, which has a specific heat capacity of 4,810 joules per kilogram per degree Celsius. This liquid is initially room temperature, around 21 degrees Celsius. The pipe is around 1 millimeter thick and made of malleable plastic, and the rate of flow is 7.5 milliliters per minute. Here is a diagram to explain the chosen approach a bit more in depth. So, to determine the direction of flow of a liquid in an opaque pipe, a heat source is placed near a section of the pipe, and a temperature gauge is placed on either side of the heat source. As the water passes through the heated section of the pipe, heat is transferred to the water. Depending on the direction of flow, one of the temperature gauges will pick up the heated water, determining the direction of flow. To test this theory, we set up an experiment. A stream of water was supplied to a small pipe. Two thermocouples connected to multimeters are attached to this pipe, and a 12-volt light bulb was placed underneath the pipe, leaving a 5.5 centimeter gap either side of the light bulb. The temperature of the two thermocouples was then measured over 5.5 minutes after the flow and heat source are turned on. Upon our first attempt, we found the difference was not very significant, so we added a black strip of tape to the pipe above the heat source to absorb the energy better, as the clear pipe was scattering and reflecting the light. This gave us much better results, clearly indicating that the thermocouple after the heat source was reading higher than the one before. To the right is a graph representing the data we collected. I'd just like to note that the colours red and blue in this instance do not signify hot or cold, they represent the thermometers A and B. To improve the device, we replaced the thermocouples with disc thermistors. Thermistors are temperature-dependent resistors, as they lower resistance when the temperature is increased and vice versa. This allowed us to measure the temperature more accurately. These two thermistors were connected to a 5-volt Arduino and were measured through the analog pins. The analog pins measure input voltages between 0 and 5 and convert them into integer values between 0 and 1023. A diagram of the setup is shown here. This circuit displays a voltage divider using two series resistors, allowing each thermistor to display their respective values individually. When the temperature increases, the resistance decreases, meaning the voltage also increases. This is how we measure the temperature using the thermistors. With some code, the voltage of the two thermistors was able to be displayed in the form of a live graph, which we'll show you in a moment. A small setback we encountered was that of the reading of the two thermistors. Initially, the two thermistors were reading different values, even though they were at the same temperature. To calibrate these, we added a resistor of 150 ohms to thermistor A, which was reading higher than thermistor B. We were also able to fine-tune the value in the code so that the two thermistors read the same value at the same temperature. Later, though, we found that taking the additional resistor out again and fixing the code calibrated the two thermistors. The data presented is only that of the data taken without additional resistors or alterations to the code. As you can see, this graph is much more accurate than the one taken with the thermocouples. The two thermistors read the same temperature before the heat is activated, just to confirm they are calibrated. The heat source is then turned on and the temperature rises. It is interesting to note that the two thermistors increase at the same rate when the heat source is turned on, and then at the peak they separate, where thermistor A reads higher than thermistor B. This is because as the heat source is activated, the pipe needs to heat up, and only when it is hot enough to transfer heat energy to the water inside does thermistor A display the higher temperature. For this experiment, the heat source was turned on while the flow was off. This was conducted to further confirm the effectiveness of this approach. When both the thermistors read the same voltage, meaning the same temperature, the flow was turned on, and the now heated water moved through the pipe, being picked up by thermistor A in blue. You can see the spike as the heat passes through, and you can note that after the spike of hot water, the temperature reading of thermistor A decreases a bit, but then remains at a constant temperature above that of thermistor B. This video is a time-lapse of the heat source being turned off after being on for a while. The flow remains constant. This shows that after cooling down, the two thermistors measure the same constant, further proving this method as effective. Here is a better look at the graph. As you can see, the two thermistors even out to the same temperature after the heat source is switched off. This graph displays the two thermistors while the flow and heat are constant. The difference between the two thermistors remains generally the same, and even despite this fluctuation, it is clear which thermistor displays the higher temperature over time, indicating the direction of flow. A bit of a reflection of this approach to the problem. A requirement of this task was to use an opaque pipe. While we did use a clear pipe for the experiment, the effectiveness after adding a strip of black tape around the pipe by the heat source was increased significantly. So, using an opaque pipe would still be effective, if not more effective, than a clear pipe. Another requirement of this task is to optimize the device for the smallest flow possible. This method is actually most accurate at a slower rate of flow, since there is less volume of water to heat up over time. It is exciting to think that with further experimentation and calculations that you could even measure the rate of flow using this method. When the rate of flow is slower, the difference in temperature between the two temperature gauges is larger. This is because the water has more time to heat up as it passes through the heated area more slowly, so it is hotter. This approach could definitely be used in real-life situations. It may not be able to be used in some medical applications or situations in which applying heat is dangerous, but it still has many applications in the real world, such as plumbing and farming. If this approach were to be used commercially, the cost would be less than some other methods like the ones we brainstormed previously. This method is also easy to set up and could be done with fairly simple apparatus. Here are a few improvements we could apply to take this approach further. An issue we thought about was that this approach would vary significantly if the material of the pipe was changed. For example, if a metal pipe were used, it would spread the heat further down the pipe, and the water may not absorb enough heat for the temperature gauges to pick up. This might be fixed by moving the temperature gauges further away from the heat source and increasing the temperature of the heat source. Another aspect to consider is a larger diameter pipe or thicker walls of the pipe. More energy would be required for this method to be effective, and more sensitive temperature gauges. Perhaps insulated temperature gauges would increase the performance, as external factors would not be affecting the reading as much. An issue with our experiment was that it worked for only very minimal flow rates, and while the question requires us to optimize our device for the smallest possible flow, a device that could measure a larger flow could also be more applicable to the real-life situations. Initially, we thought that for faster rates of flow, the heat source should be increased, but the limit of heat we could apply before the pipe melts or is damaged was a restriction. Later, we came up with the genius idea of not increasing the temperature, but rather increasing the exposure the water receives to this heat. That way, the temperature would not be too dangerous and the device would still be effective. By placing multiple light bulbs or heat sources along the pipe and covering more of the pipe with black tape, the water is able to flow at a faster rate while still having enough heat transferred to it to be able to be picked up by the temperature gauges. This addition may also allow pipes of different materials, diameters, and wall thicknesses to use the same method. A few other methods using this approach we came up with are the following. See, black tape would only be used if the heat source was that of light. Otherwise, other forms of heat could be used. For example, a strip of heated metal could be clamped around the pipe. You could also cool down part of the pipe. If heating it up would be too dangerous, it would still have the same effect. If the liquid was cooled enough, condensation could be formed on the outside of the pipe, and that way you could display the direction of flow visually. You could also paint on temperature-dependent paint that changes color with the change in temperature, and that could also be used to visualize the flow. This approach to the question is plausible and effective. I have created a non-invasive device that determines the direction of fluid flow inside an opaque pipe, and it is optimized to measure the smallest flow possible. Thank you. Any questions?